but I still encourage the audience, if you have any questions, please write it in the Slido widget and I will come back to it later. So I will give you this virtual upload and we will move to our next speaker from Brookhaven National Lab. Yeah, you're welcome. Zhiyan Wang from Brookhaven National Lab. He will give us an update about analysis status of the measurement of charm and bottom production in PHENIX. Zhiyan, can you please share your screen?
Thank you, Lamia. Can you see me and hear me?
Yes, I can see you and hear you, but I don't see your slide yet. Okay.
How about now?
Okay. Zhiyan.
Thank you. Hi, everyone. My name is Zhiyan Wang, and I'm from Brookhaven National Lab, the PHENIX collaboration. Today, I will be presenting the analysis status of the measurement of charm and bottom production in PHENIX p-gold collisions at 200 GeV. So to start, PHENIX collaboration has been using charm and bottom as hard probes for the quark-gluon plasma. And on the left, you can see the invariant yield for charm and bottom from gold-gold collision at 200 GeV published in 2016. And on the right, you can see the experimental result of bottom electron production fraction compared to the theoretical PQCD calculation from funnel. So we have it for gold-gold, and in the meantime, we have it for the PP collision published in 2019. And as you can see, for PP result, the experimental error range is within the theoretical error range. So that is good. And next, moving on to my focus is the p-gold collision. The reason for doing the p-gold collision at 200 GeV is because of the nuclear modification factor. It is suppressed for heavy flavor productions due to three, and its production is affected by three factors. The first one is the number of incoming binary nucleon collisions. And the second one is the modification of parton distribution function, which is subject to the initial condition before collision. And the third one is the suppression of heavy flavor electrons at high PT caused by color opacity energy loss. So that's mostly the collisional energy loss in the quark-gluon plasma. So the first one can be modified by the PQCD calculated binary baseline, which is for PP. And the third one can be, the information can be obtained from the hot nuclear matter, which was done for gold-gold. And for me, I'm focusing on p-gold, which will establish the cold nuclear matter baseline as to study the parton distribution function as another contributing factor to the heavy ion collision. So next is how PHENIX work for my experiment, for our experiment. On the left, we have the PHENIX detector illustration and how an electron track will go through the PHENIX detectors. PHENIX detectors are designed to measure electrons, and we have tracking and identification capabilities through drift chamber, as you can see here, and ring imaging Cherenkov detector. So our target is to measure through semi-leptonic decay instead of hadronic decay because of this high power electron identification power. And our target charm mesons and bottom mesons through semi-leptonic decay, we have one electron product from the decay, and that's our target. And our target is at high PT, which is where the physics interest lies, the suppression of nuclear modification factor. The value is around 1 GeV to 10 GeV, and we can measure the momentum of electrons through drift chamber, and we have the deposit energy in electromagnetic calorimeter. So next, since we want to measure charm and bottom production separately, we introduced the idea called DCA. So DCA is the, as you can see on the left, we have collisions happening at primary vertex, and then the mesons travel a little bit, and at the end of their lifetime, they decay at the secondary vertex. Electrons from the decay goes through the detector, banded by magnetic field, and we can trace it back through the detector to extrapolate the track. And this distance, the distance of closest approach of an electron's path to the primary vertex, is what we call DCA. Due to the different lifetime for B and D meson from bottom quarks, as you can see here, in a few hundred microns, we can make this detection possible using a detector called silicon vertex tracker. It traces back the electron's path and calculates secondary decay vertex with a resolution about 50 micron. So we have longer-lived B mesons. They are going to have a bigger DC distribution because when they travel further, the DC value tends to get bigger. So with this method, we can separate charm and bottom. Next is illustration of my research plans. First, starting with data quality assurance, data recalibration, and with the clean data, we apply electron identification cuts to obtain an inclusive electron candidate. Then, regarding this electron candidate, we plot their DC distributions according to different PT value, and also eliminate the conversion electrons to enhance it for heavy flavor electrons. In the meantime, we simulate for background DC distributions, get a template for each of possible contributing factor. And through the process, we determine the fraction of heavy flavor electron. Then we apply the fraction of heavy flavor electron to the inclusive electron candidate data, and also simulate, use a Zhiyan simulation to get efficiency for the PHENIX detectors to get a normalized heavy flavor electron PD distribution and put them all together into a process called unfolding to eventually get the invariant yield. I'll get to unfolding with more details later. So this is a data comparison for p-gold compared to PP and gold-gold. We have the integrated luminosity for PP at 23 PB inverse, and with integrated luminosity 80 nanometer inverse for p-gold, we consider the number of nucleon for gold and have a PB equivalent integrated luminosity for p-gold very close to PP, and thus they have roughly the same statistical error bar for PP and p-gold. The statistical error bar for gold-gold is on the same order, about half of PP. So next is an example of how we're doing this electron identification. So for electrons, we can measure its energy and momentum almost fully. So they are going to be at the same value. So the ratio energy over momentum is going to be around 1. But for hadrons, we can't get all the deposit energy in the electromagnetic calorimeter, so their energy over momentum is going to be very small. So this provides us the electron identification power. But to do this for all the electron candidates, we want to standardize it. So we subtract the mean of each distribution, normalize it to a mean of 0, and
2 minutes left, Zhiyan.
Thank you. Mean of 0 and sigma of 1, the standard deviation of 1. So we have a distribution on the right like this. So we can apply standard cut of absolute value less than 2 on the data to select electrons. And we have similar sorry, not similar, but another electron identification cut for using the Cherenkov light, about 20 MeV electrons generate Cherenkov light in gas, and about 5 GeV hadrons trigger the Cherenkov light. So we use quantity called N0 to select it. As you can see, the swap track has a very different shape as the actual track in this case. And we can see the clear effect of different N0 cut on the normalized PT spectrum. So for the final result, we do a process Bayesian inference known as unfolding, and to separate charm and bottom DC distribution, we subtract other sources of electrons from the total electron candidate and enhance DC distribution for heavy flavor electrons and obtain the inclusive non-photonic electrons, conclusion of both charm and bottom yields. And as you can see here, this is where I'm at with the raw yield for inclusive electron. So eventually, this is our target, to separate charm and bottom through unfolding to get DC distribution like this, and also generate the invariant yield. Right here, PP results are provided because the research is still going on. So to do next, I'm still working on the jump simulation, and then I will do the unfolding to get charm and bottom invariant yield, eventually to compare the nuclear modification factor for PP, P-gold, gold to establish the cold nuclear matter baseline, and the results are expected in August this year. Thank you very much.
Thank you, Zhiyan, for an interesting update. Thank you. I don't see any questions. And the number of online attendees increased to 60. Just quickly, if you were not with us since the beginning, so please, if you have questions, write it in the Q&A slide widget, and I will come back to it later. Since we are to remain on time, let me thank Zhiyan for his talk one more time, give you a round of virtual applause, and we'll move to the next speaker. So next speaker is, welcome, Aravindan Venkateeswaran.